Okay, I think we can start. It's a pleasure having here Professor Francesca di Lodovico from Queen Mary University in London, who will speak about us about the ghost particle and making the status of the research in the properties of neutrino particles. Francesca and I had for a long period quite a parallel career. She was in L3 while I was in Delphi, then we joined in Babar. Her interest focused since in CP violation issues, first on the hadronic sector, and then she moved to neutrino physics, always with a particular feeling for CP violation. She was in SNO, the first experiment establishing without any ambiguity the oscillatory nature of neutrino disappearance. And then she moved to T2K, where she's now responsible for the near detector, and she's also in charge of the cross-section measurement, which are an important issue for reducing the systematic uncertainties on the parameters of the Pontecorvo et al. Matrix. She's also the project leader of a to-come experiment, Hyper-Kamiokande, which will increase greatly our sensitivity on neutrino parameters, possibly discover CP violation, and maybe discover, or at least improving limits on the lifetime of the proton. So I think that this is enough, and I'm eager to hear about your report. Thank you.
All right, so allora faccio la presentazione in inglese perché appunto non tutti sono di lingua italiana qui, però se poi ci sono domande in italiano posso rispondere in italiano, oppure le domande possono essere fatte in italiano, comunque come chiunque preferisce. Allora, so I'll do the seminar then in English. So I'm going to give a report, a description of what is a ghost particle, and I think it's a very important part of our life as a physicist. Eventually I get used to this one. Oh no, sorry, it's this one, yeah. Right. Yeah, okay, sorry, I need to look at that. So neutrinos, those are the ghost particles I'm referring to. Neutrinos started a sort of a low level. They weren't known, and it took a little bit of time in the 50s up to now. This is the number of papers published as a function of the years in order to get the neutrinos as sort of a main item in particle physics. But now they are really one of the major items in particle physics. The people working in these areas received several Nobel Prizes, 5 I can count so far, and there are many new discoveries that are ahead of us. So it's really an important part of our life. Now, what I'm going to describe in the next slides is first a general review about neutrinos, what I say it's neutrinos in a nutshell. Then I will focus more, I'll just have one slide actually on the history of neutrinos, just to show what happened. And then I'll focus more on the neutrino oscillations. So I will talk about both the current results in neutrino oscillations and what we can foresee in the future. And then finally, I will show the complementarity and the synergy with other experiments. I will not describe something that is beyond the standard model, like sterile neutrinos or non-standard neutrino interactions. That will require a seminar just per se. So moving on in describing neutrinos in a nutshell, neutrinos are one of the fundamental particles in particle physics. So they belong to the particle physics, standard model of particle physics, say diagram, they are associated to, they are leptons, and somehow they are associated to the partners, charged partners, electrons, muons, and taus. And this is just a sketch of the standard model in particle physics and the corresponding antimatter. So we have something for matter and we have corresponding antiparticles. The standard model then describes the particles that exist in nature, their forces, and there are different kinds of forces. And as we will see, the neutrinos, this is why they are very elusive particles. It was very difficult to find them, and they are because they interact just weakly. So, as you can see here, right, the red doesn't work very well, but I hope you can read here. So neutrinos have spin half, they interact weakly, and they come in 3 pairs, 3 generations associated to their corresponding charged leptons. So electron neutrinos, muon neutrinos, tau neutrinos with the taus. The neutrinos interact through through weak interactions, and here you can see, so the gauge bosons, the mediators are the Z and W bosons. So one is charged, the other one is neutrals, and here are some diagrams that indicate the kinds of reactions we are looking at. So in one case we have a neutrino in the final state, in the other case we have a corresponding lepton of the same flavor than these leptons in the final state. But in order to have this one happening, I'm sorry for the slides, eventually. All right, so a lepton flavor will be produced in a charged current process only if the neutrino has sufficient energy to produce the corresponding mass in the final state. So you can't have all the times the production of a particle. Now, how can we then identify neutrinos? This was one of the reasons why it took a long time somehow to identify these particles, to measure them. So usually what happens is that we have electromagnetic interactions, for instance, that help us in identifying the particles in the final state. But in the case of the neutrinos, since they interact just weakly, and they don't have any charge, etc., it's hard to detect them. So what we can do is just to detect them as a byproduct of the weak interactions. So as what we are looking at is just to look at the final state charged particles in general. So what's happening is that we can identify them through the byproduct coming from the weak interactions, so these charged leptons. So how weak is weak? So that means that 3 MeV neutrinos, that is, for instance, the neutrinos coming from the sun, will travel 23 light years through water on average before interacting. So it's very, very hard to detect these particles. This means that, again, this is not very visible, but somehow the moral is that in the case of neutrinos, we need lots of neutrinos, so a very powerful, a big flux, and also we need a big detector. So these are the 2 main characteristics, lots of neutrinos in the flux and a big detector. Now, this is an example of natural sources we have. This is just the, basically the probability of interaction as a function of the neutrino energy. And here there are different sources. You can have very low energy neutrinos still coming from the Big Bang up to extragalactic neutrinos, very, very energetic. But in the meanwhile, in the middle, you do have all sorts of other productions through Earth, to atmospheric neutrinos, supernovas, other somehow galactic astrophysical sources, and you may have as well the human-made neutrinos, so like for instance the ones coming from the reactor neutrinos and the ones coming from the accelerators. So you do have, say, a mix both of what we can produce as humans and what we can get from natural sources. Of course, in one case, we need to build the apparatus to produce that. In the other case, we just need to have the detector to produce them. And we have less flexibility, both in the flux of those neutrinos, as well as the length, if you want, the baseline from where they are produced to where we can detect them. Now, again, going back to the discussion how we can detect them, we need a very large detectors. We need to have something that, for instance, emits light, that we can detect this light in the final state, and then that gives us an indication that we have neutrinos that have interacted with the detector. And here is just an overview, really, of some main detectors. You may have a water chunk of detectors, so you do have a water chunk of interaction, a water chunk of a cone in the final state once you do have an interaction. And this is from Hyper-Kamiokande. We'll see this experiment, we describe this, the outcome from this experiment several times in this presentation. And this detector is a big, large cylinder, 50 meters high, with a diameter of about 40 meters, that is in a mountain in Japan, 1,000 meters below the mountain, the peak of the mountain. So it's a fairly known, but at the same time, it's a fairly large, the largest water chunk of detector around. We do have, as here you can see, for detectors, for instance, these are with liquid scintillators, and these are, for instance, for detecting the neutrinos coming from the reactor neutrinos. So in that case, from reactor neutrinos, you have antineutrinos. So you detect those ones, you see the light coming from the liquid scintillators, and you say, oh gosh, I have a neutrinos. Similarly, you do have actually something that is very, very nice. It came up more it's more recent if you want. It's liquid argon detectors, where they do use liquid argon. For instance, in this case, there is also a planned, very big detector that wants to use liquid argon. And in this case, you really have tracking capabilities like a bubble chamber. So if you have in mind the bubble chamber, what you were seeing with the bubble chamber now is the same. You can also ideally do the same with a liquid argon detector. And then you have, again, something liquid scintillators, partially liquid scintillators, or something that is iron magnetized, that is more, say, a standard detector. Extremely large again, but it has a different capabilities than the other ones that are liquid-based. Now, this is in a nutshell, the history of neutrinos before we move on to the to describing the neutrino oscillations. So there were mainly two, or also three, if you want, main events. One happened in Hyper-Kamiokande that we just described. So Hyper-Kamiokande was able to observe atmospheric neutrinos. So here you have a Hyper-Kamiokande. And then here, this is Earth. So you can detect neutrinos coming from all over the places. And what you can do is to compare neutrinos depending from where they are coming from. And you can see what happens depending on the angle they interact. And this showed that there is a discrepancy between what you would expect if neutrinos were arriving and they didn't so-called oscillate, they didn't lose, say, some neutrinos were, all the neutrinos were arriving, basically the detector. With respect to what actually was measured, that shows 4 neutrinos coming from here, they show that there is a deficiency here. So that was an indication that the neutrinos coming from the bottom are different from neutrinos coming from the top. Similarly, for solar neutrinos, this was at that time the so-called atmospheric puzzle, and then there was the solar puzzle as well, because in that case, these are the this is the predicted flux of a neutrino electron coming from the sun. But this is what was observed in different kinds of detectors. So these are just different detectors with different capabilities, different sensitivity to different energies. But then arrived the SNO. SNO managed to basically identify all the types of neutrinos. And what he said is that, well, okay, we really don't have a deficit. It's just you guys weren't measuring all the neutrinos. So there was a change of flavor, so-called, changing from one type of neutrino to the other one. And then also Kamland, that was a reactor neutrino. So this experiment was getting antineutrinos coming from reactors, and then observed that the survival probability of these antineutrinos had an oscillatory behavior. So, and as we can see, this dependence L over E is the same as well. We can see in the oscillation probabilities. So now we are looking then at the neutrino oscillations. So neutrino oscillations are analogous to what happens in several fields, many other systems, in quantum mechanics. So you can expect, for instance, that an electron neutrino will eventually become an muon, or, well, it's the opposite more in general, muon become an electron neutrinos, etc. So you can see a different flavor that you may be able to observe as a function of the direction of motion. So again, like the possible states, you are looking at the mixing of the flavor states. So you have the neutrino eigenstate, the flavor eigenstate, as that is a mix through a mixing matrix that we call U at the moment of mass eigenstates. And then this is the standard evolution of the mass states. I'll be quick here, but I just want to say if you write the transition probability, if you take into account relativistic approximation, then you can, in this case, we just focus on 2 neutrino oscillations. So we are looking at what happens once we go from a muon into an electron neutrino. In this case, the probability for the neutrino muon to transform into neutrino electron depends at the first order, really, is a probability equation that has this relation. So it depends on the mixing angles that really they are the disalignment between the flavor and the mass eigenstates. You can parameterize the matrix U that I said before. Characteristics of the neutrinos that are not in that matrix, and those are the neutrino masses. So you have neutrino 1 and neutrino 2 and the corresponding masses. And then it depends as well on some characteristics of the experiment that in some cases you may be able to choose, like when you have an accelerator, when you have possibly a reactor, but in other cases, like for instance when you get atmospheric neutrinos or where you get solar neutrinos, you have less ability to choose these parameters. For instance, the length, you can't change the length. But anyway, these are characteristics that are determined by the experiments you are looking at. And this is the oscillation probability. So again, for alpha and beta, in this case, a generic, so 2 flavors as a function of L over E, because you have this dependence on L over E. And that depends, the frequency depends on the parameter, on the masses, on the square masses, and the amplitude depends on the theta. And this is so-called the first oscillation maximum, basically the first oscillation. But what I want to highlight as well is that if you are very close to the production of the neutrinos, you don't have almost any oscillation behavior. And this is important because often what happens in the detectors, in the experiments, you do have, when possible clearly, you can't do that with the sun again, but you do have a detector very close to where the neutrinos are produced and further away, where further away you measure the oscillating behavior, and close to the source, instead you say, well, now I shouldn't have any probability, any oscillation, so at this point I just see basically what has been produced. So it's very important to notice that in all the experiments there are usually these two points, something that measures the oscillation and something that is a sort of a normalization factor that is a so-called near detector. Now, what are we learning from neutrino oscillations? We are learning two important things. The neutrinos have masses. This is not something that we should give for granted. The neutrinos have a mass that wasn't hypothesized in the standard model of particle physics. You say, well, okay, but then it's easy. You just say they have a mass. That has other implications. So it's not obvious to really to say, well, we want to have now the neutrinos with a mass. So this was very important, as well as the fact that they mix as well. That depends on this matrix U. And so we can measure the parameters in U, as we will see in a moment. And actually, the fact that the neutrinos have masses is the first evidence of physics beyond the standard model that we have, beyond the standard model of particle physics that we have observed so far. Now, continuing in our description of neutrinos, let's look at what happens at the moment as far as our current knowledge is concerned. So the neutrinos from the sun have been extremely important as neutrinos for discovering that there are oscillations in neutrino experiments. So they have been extremely valuable for that. But then we can further try to understand what's happening. So in this case, the solar radiation, okay, there are 2% of neutrinos, and here you can see the corresponding processes. The typical energy for neutrinos is fairly low with respect to standard energies for at least particle physics. So they are fairly low, of the order of 0.1, 10 MeV. And here it shows the different, again, reactions from this diagram as a function of the energy of the neutrinos, where these are the reactions, and these are the regions that are investigated by different types of detectors. So if you remember before, we were looking at the different detectors, and the difference is that they have different abilities in some ways. The threshold, for instance, for neutrinos, for the neutrino energy could be different. And for instance, water Cherenkov detectors have a threshold at the moment about 4-5 MeV. We can go much lower with the scintillators. And here it's actually we can look at the we can look at the current experiments in the same diagram, where the sensitivity as a function of the energy is shown. In particular, this experiment is able to go very low in the energy, so to explore the PP reactions as well, Borxino here in Italy. And then Hyper-Kamiokande, we already described before, as know, are able to explore as well this region that is very important because it indicates that the neutrinos pass, the solar neutrino pass from the vacuum and average enhanced to a matter-enhanced oscillations. So we'll look at the matter in a moment, but this indicates that in some cases, in some ways, we are moving from one kind of neutrino oscillations to another type of neutrino oscillations. And here are the latest results from Breuer-Exino, again as a function of the neutrino energy and for the different interactions. So they managed, Breuer-Exino managed to go very low in the energy, and this was extremely, it's extremely valuable, and it's an experiment that can give much more in the future as well. Now the atmospheric neutrinos, again, we touched on the atmospheric neutrinos before, and these come from cosmic rays that hit the atmosphere that produce pions mainly, that decay producing muons and electrons and corresponding antineutrinos, neutrinos and antineutrinos. So you can see that one in this diagram. Now the typical energies are much higher than, are usually higher, but can become much higher than from solar neutrinos. So from 100 MeV to 100 GeV, so extremely, extremely high or even higher. The typical distances can be very high, of the order of 10,000 kilometers. And what happens is that these detectors, in this case, super K, as we saw before, but also other detectors. So we may have something in the South Pole, we may have something in France, we may have something somewhere else in India. They do detect neutrinos coming from all over Earth. Depending on the direction of the neutrinos, the detectors manage to understand from where they are coming from. This is the updated distribution from Hyper-Kamiokande. Again, this is neutrinos going upwards, neutrino going downwards, and you can see that there is a deficit here with respect to the predictions in case you would assume that the distribution is totally uniform. And this is another experiment that is actually in the South Pole, and again, you will see the same behavior, although this is a function of a length over energy. But this is a clear evidence of neutrino oscillations again, and then now we are just trying to improve much more, not just for the sake to improve that, but because it's relevant for other determination of observables. Now, reactor neutrinos are neutrinos that are produced from the reactors. Actually, we produce electron antineutrinos. The typical energy is fairly low, of the order of 3 MeV. So we just have electron neutrinos and antineutrinos and the electrons in the final state, and they are detected through the so-called inverse beta decay. So a typical reactor neutrinos have the antineutrino electron that hit the nucleus, and then you do have the electron that is, or anti-electron that is positron that is ejected, and you do have the neutron then that is absorbed by an isotope that could be usually gadolinium. So you do have two hits basically in the detector that identify, that indicate that you do have an antineutrino that has hit the detector. So what are the typical distances here? You can't choose the energy of the neutrinos, but you can choose the distance, how distant you are from the neutrino reactor. And at the moment, we do have reactors at a distance of about 1 kilometer that will show Diabei Reno, we will see in a moment, and or we are building neutrinos detectors around 60 kilometers. There are, to be honest, there are other detectors that are much closer. At the moment, they are being built much closer to the source than 1 kilometer, and this is to explore sterile neutrinos. But again, this is something that goes beyond this presentation. But we do have other distances that are not described here. So in this was extremely important, especially this experiment here is very powerful. In 2012, there was the first measurement of the anti-neutrino disappearance. This observation has very important implications for the future neutrino program and the understanding of the origin of mixing. And it's related to CP violation. You can't have CP violation if this term was equal 0. But the CP violation, again, is something we will see in a moment. These are the three detectors, main detectors I mentioned. So you do have, this is in France, this is that will show. This is in Korea, this detector. So you can see here the power plants as well. And here this is more complex, it's Diabay, where you have different power plants. And the location of the so-called near, as we were saying before, and far detectors, where these ones basically give you the normalization. And the far detector gives you the measurement. The oscillation probability for antineutrinos disappearance, where I mean that we know how much they are produced in the reactor. What we want to see is how much we detect after 1 kilometer. Is this formula here was distribution, the probability, so-called survival probability or disappearance, as a function of the length is shown in this plot. And the detectors are around 1 kilometer from the source of the detector. The source, sorry, of the antineutrinos. So these are the three detectors. This is something more complicated, we'll see in a moment. And this is the evidence that there is a disappearance of the neutrinos. So the neutrinos disappear, the antineutrinos. So this is from Diabay, and this is really the evidence that this oscillation happens. But especially this term is not 0. And this is important because then will allow us to measure CP violation. Now, we discussed so far the neutrino oscillations, looking really at what happens in case you do have just 2 flavors. But let's see what happens in case you have 3 flavors. You do have to multiply the matrix to have 3 rows and 3 columns, obviously. And this is called Pontecorvo-Maki-Nakagawa-Sakata matrix, PMNS mixing matrix. If you are familiar with the quark sector, it's really the analogous to what happens with the CKM matrix. So you have the CKM matrix in the quarks, you do have the PMNS matrix for the neutrinos. And again, like for the quarks, you can parameterize this matrix. This is the product of 3 rotational matrices. And this is quite important because you can really factorize the so-called atmospheric and the solar neutrinos, like mainly dependent from this part of the matrix and the atmospheric from this part of the matrix. This is why before they were analyzed like 2 flavor oscillations. And whilst the intermediate part depends mainly, is measured mainly by a reactor along baseline neutrinos, as we will see. This term here, so we can parameterize all these metrics. This one here can be parameterized in terms, it's a unitarity matrix, and can be parameterized in terms of 3 rotation angles and 1 complex phase. These are theta 1, 2, theta 1, 3, and theta 2, 3 that you saw in the previous equation. So sorry I didn't introduce them yet, but those are parameters of this mixing matrix. And then delta. Delta is the complex phase, and this is the CP violation we mentioned a few times. And these, the neutrino behave differently from antineutrinos. So if they do, these should be not 0. Now, what does it mean? At the beginning of the universe, there were lots of particles, and we assumed that the particles and antiparticles exist both in abundance. But now, no, now it's not happening the same, now it's different. And what happens is that particles and antiparticles annihilated, leaving behind a universe dominated by matter. So the CP may hold the key to explain what happened. So we don't know yet. We don't know even what is the value, but this may be possibly explained by CP violation in the electronic sector. And from the point of view more pragmatic, how are we able to measure CP violation? So this is the probability, again, of oscillations from P mu into, of a muon neutrino into electron neutrino. And this is for neutrinos and antineutrinos. This is, again, the probability of oscillation. And what we can do, the oscillations probability, that depends on delta. They have different, all these diagrams here you see that depend on delta. So what we can do, and the effect also is different depending on the different values of delta. So we can do is to first compare whether the two give the same result, neutrinos and antineutrinos, and then try to understand how much is the difference between neutrinos and antineutrinos. That could be fairly sizable. What is the standard way in which then we try to measure CP violation? That is through long baseline neutrino experiments. So what is a long baseline neutrino experiment? You produce the neutrinos through an accelerator. So you have muon neutrinos that are produced from the decay of pions, charged pions that are produced from the interaction of a proton beam with the target. So you do have a proton beam, you have a protosynchrotron, you interact this target, you have pions, you have a decay pipe, and you have at the end muons that you remove, and muon neutrinos. And you use those muon neutrinos, and you have these neutrinos crossing Earth. This may be more or less long, this baseline, but then you have them produced here and detected at several 100 meters or several 1,000 meters, depending really on the experiment. There are a few of these experiments. This one already stopped data taking. This one and these ones are running. These ones already stopped. And these are the two future experiments, DUNE and Hyper-Kamiokande, where Hyper-Kamiokande is actually in some ways the evolution of T2K, whilst DUNE is totally new. And the typical energies vary as well depending on the experiment. You may have something around 700 MeV, 600 MeV, like in this case, first case, or you may have something much higher, like in this other case, 20 GeV. So they also, these experiments were important because not just the reactor neutrinos were able to measure theta 1,3, but also these guys here were able to measure theta 1,3. Now, I'll be quick in these slides, but I just want to show what happens if you have neutrinos and antineutrinos, and you look at both the neutrino and disappearance and the neutrino appearance, and similarly neutrino disappearance and neutrino appearance. So it's hopefully you can still read these ones here. You do have the neutrino disappearance of muons, but you have also the appearance of electron neutrinos for neutrinos and antineutrinos. So you can see that we have several hundred events. If any one of you is working in Atlas or CMS, of course we are dealing with a much lower number of events, but still it's extremely important that we are able to determine, to measure these processes. And then we may again look at CP violation. These experiments don't have enough power or enough big detector, and they are suffering from systematic errors in order to measure CP violation. But still, they are very powerful because we can exclude at least several level whether we have CP equals 0 or not. So those are very important. But the future experiments, Hyper-Kamiokande, DUNE, as we will say, will make an observation and precise measurement of this parameter. Now, just to summarize the parameters, the current neutrino parameters. So this is just a fit that happens, that has been made by this collaboration, NuFit, to all the available data. And they then look, they made a global fit. So we, since all the different probabilities have dependencies on different parameters, and these are the results for depending. In this case are the angles. In this case is delta m square. The two delta m squares in this case is delta Cp. But let's focus on these ones. So these angles are fairly large. They are larger than if you are in the quark sector. That is a difference. Quark and leptons and neutrinos are fairly similar for the process, in some ways for the framework, but they are very different from the point of view of the results, really. If we look at, then we have measured then these angles, so let's look then at how we can represent in terms of the mass eigenstates, in terms of the Flavour eigenstates, what is the composition. And this plot really, these plots show you, for instance, that in the third neutrino, you do have just a small component of neutrino electrons, while actually you have a much larger component of neutrino muon and neutrino tau. So these are very different among themselves. Regarding the masses, again, they are very small masses. The thing to notice is that delta m squared 3,2 is not defined as far as design is concerned. Why? Because in the probability equations we have a module. We have an absolute value. Can we measure that? Can we have other? Can we try to resolve that? We did that for the theta M12. Why don't we do that for M32? Yeah, we can. We'll address this one in a moment. And what is the implication, really? Why do we have two solutions? So we have two solutions because since we are unable to determine the sign of delta m squared 3,2, that is the difference, the square difference of the masses, the difference of the square masses, we may have two possible orderings. In one, the order is that m1 square, m2 square, and m3 square follow what you would naively expect. So m1 is the one with the lowest mass, m2 the middle mass, and m3 has the highest mass. But in this case, it's the opposite. It's different. You assume that delta m square has a negative sign, and then so you have the order m3, m1, and m2. In this case, you called normal hierarchy or normal ordering. In this case, you have inverted hierarchy or inverted ordering. So normal is really what you would expect naively. Inverted is what happens because you don't know the sign. And again, CP violation, it's again measured by, or anyway fit by this program. Now, how can we try to address these questions? The opening questions, again, the mass ordering, the CP violation, we didn't address this one, we'll not address that, but theta to 3 is about 45 degrees, and at the moment we don't know yet whether it's 45 degrees or bigger or smaller. And then we have, of course, beyond standard model neutrino mixing, like sterile neutrinos that are beyond this presentation. So the mass ordering, it's relevant to describe the model building for neutrinos, as well as CP violation. That could be the key to understand the matter-antimatter asymmetry. But, okay, how can we address then the mass ordering? I said before, well, you do have a probability equation that in that case depends on the square term. So can you, the absolute value, can you do something different in order to avoid that? Yes, what you can do is to use the Earth, really, the matter. The moment in which there is a matter, it breaks somewhat the degeneracy because you do have electroneutrinos in the matter. So not all neutrinos will interact in the same way with the matter, and the probability equation becomes a bit different. So If you look again at the two Flavour oscillation, it's the same formula, but these are tilde. And this means that the formula is a bit different. That depends really on the matter that is crossed by the particles. So what happens is that you can use the matter. This is the same that happened in M1-2 in order to solve this degeneracy and try to understand whether whether we have a normal or inverted hierarchy. This is just an example of the probability equation if you have antineutrinos, if you have a cosmics through the Earth, crossing the Earth, you have a car, you have a mantle, and then you can see the effect due to the car and the mantle, the resonance due to the presence of the matter. So, and this is very important. You can use that to distinguish the behavior of neutrinos depending on whether they have normal or inverted hierarchy. So this can help us, and there are experiments that are doing that. It's quite they are quite in very nice places actually, or anyway very challenging. This is in the South Pole. This is called Pingu. It's not running yet, but this is very nice. You do have some strings with photosensors that go below the ice. There are many photosensors. There is a sort of dome with several PMTs, photosensors in a sort of circular form that are then put in these holes in the ice. And these are the strings. But you can do, and this is what happens in the green and what will happen as well for Pingu, you can have more of these PMTs, so more strings, less separation between them. The reason for that is to try to measure lower energy atmospherics, because when you have something big like this one that is already existing and is called ice cube, you do manage to detect particles, you can see here, but they are very high energetic particles. Well, if you want to detect something that has less energy, you need to have more strings. You need to have more, somehow, detection material. And you do add more PMTs, and this is underway. Similarly, the Mediterranean, again, in South France, is again a very nice location where to put a detector. You do have strings, they're not very visible, but again, it's the same principle. The detector is slightly different for these PMTs that you put in these strings, but the principle is the same. You have strings that go down the sea, and you use the sea as what you would have done with Hyper-Kamiokande. You do have the interaction of neutrinos with the sea, with the water, and then you do have the light coming from there, and then you are able to detect that. And here is the light, for instance, from one interaction in the ice. Here you would see something similar. And again, the same principle. Here you need to put more strings if you want to detect something that is at the level of needed for detecting, for measuring the mass hierarchy. So bottom line is that they were built already, they're already existing. We have already results from these experiments, IceCube and the KM3 net. So the ones with the very large strings, but and they are very useful. But if we want to detect the mass hierarchy, we have to have something more dense, and this is happening. There are also other ideas, for instance, solid detector in India, and the same long baseline far detectors can be used. So for atmospheric neutrinos. So if you look at the another alternative is when you have these long baseline neutrinos that cross Earth. So you saw before that you may have the neutrinos crossing Earth, and then you detect them at a certain point, and then this happening. This means that you do have this means that you may have again you do have again an effect due to the matter. Finally, there is a third idea that is to use again reactor neutrinos. You put yourself in a position that you are able to at higher distance from the source, where you're able to distinguish between the inverted and mass hierarchy. But you need a very good precision, a very good resolution. And this detector is very, very precise. It's being built, and it's called Juno, and also this department is in Juno. Juno. And then this is the summary. This is, I want to show here just one thing, is that this is the sensitivity of the different experiments as a function of time. You can see that these ones are the different experiments. It's a little bit old, this one, but it wants to indicate that at the moment we mainly have nova to determine the mass hierarchy, but then we'll have the other detectors as well. So we assume that in the next decade we'll be able to determine mass hierarchy. Similarly, for CP violation, what happens? What are the next experiments? We do have two main experiments that are in a pre-construction phase. There is quite a lot of work. There is a project that is ahead, and we are in the phase of approval of the funding for both experiments, Hyper-Kamiokande and DUNE. And how they look like? This is Hyper-Kamiokande. It's similar to T2K, so it crosses Japan from one side to the other side, where instead of Super Kamiokande, you will have a 20 times bigger detector. You do have as well the possibility to detect this detector in these neutrinos in Korea, and this is a fully international collaboration where you have Japan, Korea, that are using the same beam. This is currently underway, and just to notice that this length, that is about 1,100 kilometers, is the same length of Italy, so it's quite funny to say that this would be the same long baseline that would be Italy. And similarly, you have it for DUNE. For DUNE, you do have a much longer distance than in T2K in Japan, although it would be the same length as the one in Korea, and you do have this challenging new detector that uses the liquid argon. And I just want to figure out, to mention that even in this case, well, if you look at the sensitivity, the fraction of the phase space detected as a function of time, it becomes about 80% after 10 years. And at that point, you need a smarter idea to reduce the systematic errors. So even in this case, you do need something else to go beyond the current experiments. But they will be able almost to determine totally, to span the total range of delta CP. I just want to mention that although the primary aim is to measure CP violation, these experiments are fairly expensive, they take lots of time, and they will be able to do much more physics than just the oscillation physics. I do have two things I want to mention that I will be fairly quick. We have a neutrino mass measurement, and these are, we don't know the neutrino mass, we don't know the mass ordering, but at the same time, we don't know even what is the neutrino mass. And this we can do, for instance, looking at the tritium decay. This because at the end point, this because the end point would have a different shape of this decay if the neutrino would have a mass different from 0. So you can look at these ones at this distance, but you need an extremely precise detector. For instance, this one in Germany, Katrin, maybe the next one to go. There are others, other technologies, but this is extremely challenging. The other thing I want to mention is that there is another, this is the last one before the conclusions. This is, there are the neutrinoless beta decay, where you do have, where you're exploring the nature of neutrinos. Are neutrinos really Dirac particles or they are Majorana particles? Where the difference is that in the case of Majorana particles, Dirac particles are like, for instance, other standard model particles. Majorana means that the neutrino is the same as the antineutrino. And what happens in that case? You can have so-called neutrinoless double beta decays. In this case, you do have the exchange of a neutrino because now the neutrino is the same particle. And if you look at this kind of processes, if you do have a nucleus that decays through a double beta decay, and then you look at this spectrum, then if you do have a spike, that means that in this case you do have not a continuous spectrum due to the normal process double beta decay, but a neutrinoless double beta decay, where you do have the exchange of neutrons. So this is what I wanted to mention. And just to finalize, we have looked at many experiments, we have many technologies, we have many ideas, but they are often complementary. So as you can see with neutrinos, atmospheric neutrinos, you have long baseline neutrino experiments that measure similar parameters. And I think this redundancy is also important because not always you may find the same numbers, not always you may find the same results. And we have seen with physics, for instance, we do want to have more than one measurement, and not just physics, pure physics. And finally, the conclusions. The neutrinos are the most elusive particles in the standard model. No mass, no charge, almost no mass, no charge, but they have been giving us a lot of important information. They are really the first evidence of physics beyond the standard model. And I think there will be an exciting time ahead of us. So it just started and we are looking for making more headlines. So that's all for now. Thank you.
Thank you for this very comprehensive and exhausting review. Questions? Well, I have a question more of theoretical nature rather than experimental one. However, you made it clear that even if we could simply add a mass term to the standard model Lagrangian to allow for neutrino masses, this would bring some other problems. Can you just mention which problems would be there?
Yeah, you will have the right-handed neutrinos as well. You will have the very heavy partner of the neutrinos that at the moment you don't have. So you will have a right-handed neutrino associated to that.
So the problem is having inside the standard model particles that
so
you
that
don't expect to ever see.
Exactly, yeah.
I see. And then another question. Can atmospheric mu neutrinos be used for CP violation measurement?
Yeah, they can be used actually. I can show, of course. It's just that you need many more neutrinos than actually what we have with the current detectors. At least Hyper-Kamiokande or even Hyper-Kamiokande is looking at the measurement of CP violation with atmospheric neutrinos, but the sensitivity is not as good as for Hyper-Kamiokande with a beam. But you can combine the two. So yes, we can, it's just not very powerful, but you can combine everything.
So the question
together.
is that you don't have enough atmospheric neutrinos.
Yeah.
That's
there are a lot more, there are not enough. That's correct.
Okay. Any other question? Yes, please.
Could you perhaps comment about the possibility to test non-standard neutrino interaction and eventually at which level?
Yeah, so standard neutrino interactions, they are mainly investigated at the moment, I guess, the experiments that are trying to probe these ones are at the moment are mainly DUNE and Hyper-Kamiokande, but Hyper-Kamiokande using the Korean detectors. At the level, I can't comment on the actual numbers from that, but that will be explored. That can be explored by both the DUNE with the fire detector and the Korean detector in Hyper-Kamiokande. So.
Thank you.
Yes, please. Wait a moment, please. The mic is arriving.
Thanks. Do we have any chance to detect neutrinos from the Big Bang in our lifetime? I mean, relic neutrinos from Big Bang.
Yeah.
Is there any chance to detect them through our lifetime? In the next 20, 30 years, 40, 50, I don't know.
Yeah, relic neutrinos, yes. Again, in this, I don't know, perhaps even Hyper-Kamiokande, you need to have a more powerful detector than what you have now because the background, that you have a very low energy neutrinos. So you need to have a detector that doesn't have enough somehow background. You need to be able to go a low energy and remove the background. But possibly, yes, with the addition of gadolinium to Hyper-Kamiokande, at least one tries.
You mentioned that CP violation is relevant for matter-antimatter asymmetry. So why a measurement on neutrino can help to understand this asymmetry?
Because you need a process to okay, it's one of the conditions from Sakharov for the CP violation, to happen the CP violation. But what happens is that you need a mechanism to change the decay of baryons once you do have to have an asymmetry in the decay of the baryons in order to have an asymmetry between the matter and antimatters. And this can be addressed through leptogenesis. So what happens is that you need to have a process that allows you to change the decay of particles, baryons in this case, and create baryogenesis. And that's done through leptogenesis. So basically you could have done that with the quarks, but their CP violation is not high enough. So you do have a mechanism that passes through the leptons through leptogenesis, and that affects the decay of the quarks, basically.
What value do you expect to observe in the experiment? Say yes, okay, this explains.
This is so at the moment. To be fair, at the moment we are having we are expecting that is maximum. So the maximum values that we could expect in CP violation in the lepton sector. So that's maximum. So the question is whether that is enough for the theory. I mean, for the current theory in leptogenesis to explain matter-antimatter asymmetry. It depends, I think, on the. To be honest, I'm not 100% sure, but I think it could be a possibility. Yeah, I think it could be, but it depends on the theories as well, because there isn't just one way to do leptogenesis.
Okay, last question, because time is running.
Okay, just a curiosity. I saw in one of the first slides that high-energy neutrinos can be generated by extragalactic sources or processes. What kind of sources can generate this kind of neutrinos?
You may have, I think, to be honest, actually, this is something a little bit to be investigated. What happens, the truth is that what you do have is that, so you may have so the truth is that what we have been observing are neutrinos of the order of beta PGV, and what we are trying to understand is from what extragalactic sources they are coming from. So in some ways we are reversing the problem. Extragalactic in this case, I think that's a question mark actually from where they are coming from. Yeah.
So it can be a background of neutrinos that
Well,
we
they
are
are too
observing.
high for us, but so what we did was to measure some in these detectors that are the ones in the South Pole. Some very, very energetic neutrinos were measured, and the thought is that these are extragalactic neutrinos. So the question is that how can we interpret that? And this is on the way. There are just 5 events or something. So
Okay.
they're not a background. We are measuring them, and we need to try to interpret that.
So they are distinguishable from Big Bang neutrinos basically because of the energy.
Yeah,
Okay.
yeah.
Thank you.
Okay, so I think that this is enough. Time is running. And let's thank the speaker again.